Welcome to this video for Module 3B of MCET 450, Advanced Mechanics. In this video, we will get an overview of the principles associated with beam design analysis. As usual, we will kick off this module with an example of an engineering disaster. In this example, the roof of the Kemper Arena in Kansas City collapsed when it was overloaded during a major storm with 70-mile-per-hour winds and heavy rains due to insufficient water drainage. Since the arena was not in use at the time, no one was injured. The first thing we need to do is to define a transversely loaded beam. This means we have effectively a horizontal beam member, as shown here, and it is supported at either one or both ends, as shown here. And it carries a load, such as this load here, which is a distributed load. The load direction is perpendicular to the beam's longitudinal axis. Note the longitudinal axis shown here in the image. The load may be a single point load, a distributed load, such as this one shown, or a combination of loads, or even a load that is offset from the longitudinal axis, but still connected to the beam. The loading causes the beam to bend relative to its supports. The loading also attempts to shear or cut through the beam. Depending on how the load is applied, there may also be twisting, that is torsion, on the beam. In the image to the right, we see three diagrams. The first is the free body diagram. Note that the beam is shown simply supported with two reaction points, here and here. There is a distributed load along the entire length of the beam. The length of the beam is denoted by the variable L, and the variable X is used to denote specific locations of interest along the length of the beam. The lowercase w shown here is the applied load or weight. However, in beam diagrams like this one, lowercase w indicates the weight per unit length. Uppercase W is the total weight, which is equal to the weight per unit length times the total length. Below the free body diagram is the shear diagram. This represents the shearing loads applied to the beam. Variable V is the shear force, not stress. In some setups, the shear force V is equal to the applied load, W or P as the case may be. However, for a beam setup like this one, V is 1/2 the total load and equal to the reaction at either end. The shear diagram starts at the left-hand side of the beam and moves along the length. We have an immediate spike in shear load right at the left-hand side due to the reaction at that point on the beam. Then the shear load gradually decreases until it comes to this point where it is effectively zero. But the shear load continues to decrease until we have a negative shear load at the far end, and then we have the right-hand reaction, which pushes the shear load back up and it returns to zero. A typical shear diagram will always start and end at zero. The point where the shear diagram crosses the horizontal axis right here is a critical point. Where the shear is zero, the bending moment is maximum. The area of either triangle tells us the bending moment magnitude. The horizontal axis has units of length, and the vertical axis has units of force. So if we take the area, we have force times length, which is the definition of a moment or a torque with units of Newton meters, for example. Below the shear diagram is the moment diagram. The moment diagram results as an integration of the shear diagram. It also progresses along the length of the beam from left to right, and you will notice that the moment gradually increases from 0 and maximizes at the same location where the shear diagram indicates 0. Then the moment diagram generally decreases and comes back to 0. For moment diagrams, clockwise moments are considered positive. And remember, this is opposite from the way we normally treat moments in equilibrium equations, where counterclockwise is positive. Shear force, represented by the variable V, is the sum of all shearing forces acting on a beam from the left-hand side up to a given point of interest. This is not the same as shear stress, since the area of the beam is not being considered. The moment M is the algebraic sum of all moments and couples located between the section and one of the ends of the beam. Notice the image on the bottom right. Beam moments are positive when the bending is concave upward and the upward surface is in compression. Beam moments are negative when the bending is concave downward and the upper surface is in tension. Note that this is the opposite sign convention compared to equilibrium equations. In most cases of loaded beams, bending stress contributes the most to the overall stress. Since the maximum moment drives the bending stress, it is critical to be able to determine the maximum moment on the beam. The method of creating the free body diagram, followed by the shear diagram, and then the moment diagram, allows us to use a graphical method to determine maximum moment without any other tools or computations. The other options are to either double integrate the functions, look up values from tables, or use analytical software. The beauty of the graphical method is that it works for nearly any load configuration. A common mistake made by students in finding the maximum moment is the assumption that it is the force applied times the length of the beam. That is only true for cantilever beams with a single load at the end. If you check the beam table references provided, you will find that each load and support has a different formula for maximum bending moment. But not every situation is covered in the reference tables. However, with the graphical method, you can solve for maximum moment for virtually any setup. Another area for caution: you must be sure that you are analyzing a bending moment and not a torque in these situations. Remember, bending moments deflect the longitudinal axis of the beam, whereas torques twist the beam around its longitudinal axis. Here's an example where we will create a shear and moment diagram. This is a simply supported beam. A simply supported beam has one side that is pinned, so it cannot translate up or down or side to side in the 2D plane. However, it can rotate about the pin. This constraint is represented by a triangle on the left-hand side. The opposite end of a simply supported beam has a roller support. This support prevents vertical translation, but allows movement in the side-to-side direction. Thus, as the beam deflects in the middle, the right-hand side pulls inward. This constraint is represented by a circle on the right-hand side. We have two sets of loads on this beam. One is a concentrated load. The other is a distributed load. We can conceptualize the distributed load as a concentrated load when we create our equilibrium equations. However, we must revert to a distributed load for the shear and moment diagrams. Note the equilibrium equations shown here. we find that we have a reaction of 22 kilonewtons at the pin support and 18 kilonewtons at the rolling support. We'll get back to our example momentarily, but let's take a minute to review the rules for shear and moment diagrams. If a shear load is acting upward, then the shear is considered positive. Downwards is thus negative. So reactions at either end of a simply supported beam with a downward load are positive for the shear forces. Concentrated loads are simply vertical lines, whereas distributed loads are straight sloping lines. The gaps between loads are simply horizontal lines. So in this example here, we have a reaction at the left-hand side, so we have a straight line up. Then we don't have any other loads until we get to here, so therefore it's just a straight horizontal line. But because we have a distributed load, now we have a straight sloping line, and it comes all the way down to here. Then we have no more loads till we get to the next point. So we have a horizontal line, we have a reaction, so we have a vertical load up. Again, no other load, we come over, and then finally we have this concentrated load at the end that comes down. For the moment diagram, clockwise moments are positive. The magnitude of the moment corresponds to the area under the shear curve. Maximum moment occurs where the shear stress crosses the zero line of the shear diagram. Concentrated loads are straight but sloping lines, whereas distributed loads are parabolic. Note the diagram here. So it parallels the shear diagram. So here we have a concentrated load, which was a straight vertical line on the shear diagram, but it's a straight sloping line on the moment diagram. Where the load is now distributed, that's where we have a parabolic curve on the moment diagram. And then once we come to the end of the distributed load, it becomes a straight line again until we get to the next load. Now back to our example. First, let's focus on the shear diagram. I have drawn the diagrams on the left so that they all line up underneath each other. And then I've taken screenshots of the shear and moment diagrams a little bit larger on the right-hand side so they're easier to see. So let's take a look at the shear diagram and note how it follows the free body diagram over here. The vertical axis on the shear diagram is the magnitude of the shear force. The horizontal axis is the distance along the beam. So we have a 22 kilonewton reaction on the left-hand side. It's a concentrated load, so it's vertical up to this point. Then we don't have any other loads until we get to the 24 kilonewton load. So we have a straight line until we get to here, and this is obviously a negative 24 kilonewton load. So this being concentrated is a straight vertical line. It pushes us back toward the 0 point and actually beyond it by 2 kilonewtons, right? Because this was 22 and now this is negative 24. So we go just below the horizontal line. Again, we don't have any other loads until we get to the distributed load. So right at the start of the distributed load, now we start our straight sloping line. And it goes until we reach the maximum value of the distributed load. Then finally, we have the other reaction, which is 18 kilonewtons. So we were at -2. We did another -16. That puts us at -18. So then the positive 18 brings us back to 0. And that's usually what we want to see with a shear diagram, that it starts at 0 and ends at 0. Once we're done drawing the shear diagram, we need to calculate the area of each section, because that area is going to drive maximum points on our moment diagram. So let's take a look at how we create the moment diagram. Again, we start from the left-hand side, and we effectively have a clockwise moment. Therefore, it starts out going positive. It's a concentrated load, so that means it is straight but sloping, and it goes up toward the maximum. The maximum at this point is the area under this curve, which is 22 kilonewtons times 1 meter. So therefore, it's 22 kilonewton meters, which we see right here. Then we don't have another load until we get to the distributed load. So that's going to be a straight line, and it's going to be sloping down the area under this portion of the curve, which is minus 2 kilonewtons times 1 meter, so minus 2 kilonewton meters. So this goes from 22 to 20. Now we get to the distributed load, and so now we have a parabolic curve. And it continues going until we get back to 0 here. So that would be the area under this portion of the curve. Now, don't just assume it's a single triangle, because you do have this little straight section here that forms a rectangle. But that value is what reduces us the remainder back to 0, because we have the triangle, which is effectively 16 kilonewton meters, and we have that little rectangular section, which is 4 kilonewton meters, which is a total of minus 20 kilonewton meters, which brings us from the positive 20 back to 0. Okay, so we're going to stop the video here, and when we're together in class, you will get a chance to create shear and moment diagrams and practice this. Thanks for watching.